So welcome back to this session on seismicity in the central and eastern North America. We're going to be getting started again now shortly, and we have one talk that has not been loaded, so there will be a little disruption in the program. I apologize for that, but I think we will be able to finesse it. And since it is just now after 4 o'clock, I think we should probably try to stay on schedule. So our next talk is an invited presentation by Gail Atkinson, with co-author with Dave Bohr, Developments in Ground Motion Modeling in Eastern North America.
Well, good afternoon, everybody. I see we're getting rather thin on the ground here, so this is a special plea. My PhD student is giving the very last talk of the day, so any of you who want to hear a really interesting talk should hang around. But in the meantime, I'm going to talk about developments in ground motion modeling in Eastern North America. Next slide. And the brief overview of this talk is, and why this is important, is ground motion prediction equations, which are kind of the backbone of seismic hazard analysis, rely on a lot of semi-empirical models of the ground motion. In particular, we need a model of the source spectrum and how it attenuates with distance in both magnitude and frequency space. As we gather more data in the East, we find increasing evidence, and I'm going to present some of this today, that some of these models are actually more complicated than we previously realized. And I'll give you the conclusion right at the beginning and come back to it at the end. The main conclusion is that we really don't understand very well what an earthquake source looks like in the East, and furthermore, we don't really understand how earthquake ground motions in the East attenuate, other than at regional distances. Next. So the standard models that we rely on to help us with ground motion attenuation are at the source side. Typically, quakes are modeled by a simple Brun omega squared point source model, although sometimes a double corner frequency model, a deviation at intermediate frequencies, has been proposed. And then this source model is attenuated with distance using simple functional forms, typically something like 1 over r, the hypocentral distance, if you're in close to the source and you're looking at direct wave attenuation, as you would expect from a homogeneous Earth. Or often we see attenuation that appears to actually be quite a bit steeper than 1 over r if you're in close. Then eventually we start to see some transition to the LG phase at regional distances, somewhere between 50 and 120 kilometers. We get reflected and refracted arrivals coming in from the MOHO, and by the time we get out to regional distances beyond 100 kilometers, we expect waves to attenuate roughly as 1 over the square root of r, a surface wave type spreading. The other, as well as the geometric spreading, the other factor that's important in attenuation is the quality factor, or its inverse, the anelastic attenuation factor. And this attenuation parameter is the easiest one of them all to quantify. In fact, it's probably the only attenuation parameter that we have a really good handle on, because we can get it from data at regional distances, which are what's plentiful in the East. Next. So the problem with our different source and attenuation models is that they're very non-unique in terms of what they predict for ground motion amplitudes. And this is a slide that shows, for a typical earthquake, the magnitude 5 earthquake that happened in Osable Forks, New York in 2002, we had a bunch of ground motion observations at regional distances, 100 kilometers and beyond. And if one's saying, well, how do those compare to what you would predict if you use different stress drop levels with a Brun source and different attenuation models? That's what all the lines on the figures are, and I won't go through the details of those models, other than to say that each one of those lines corresponds to a different published attenuation model for the East, and a different value of the stress drop, the main source parameter, that would fit the observations with that attenuation model. And the main point here is that the value that you would infer for the stress drop of that earthquake based on the regional observations goes anywhere from a low of 40 bars to a high of 180 bars, depending on which attenuation model you choose to believe. And they all give about the same ground motion predictions at regional distances where they're constrained, and so we really can't say much based on these observations about which value of stress parameter might be right or not. Next. So I'm reporting on updating the database in the East to look at what our current understanding of attenuation is and what it might say about source. And so I'm looking at the area shown on the map here where all the little black dots are stations from the combination of sources, the Southern Ontario Network, the Canadian National Network, and the U.S. networks on the south side of the border. And then the colored dots are earthquakes of different sizes that have happened over the last decade or so. Next. So if we look at the distribution of data that we now have accumulated in this area of the East, this is what it looks like in moment magnitude and epicentral distance space. And I focus here on moment magnitudes of 3.5 and larger. And you can see that we've got a pretty good distribution with distance at the sort of low magnitude level. They get sparser as we move up in magnitudes. I also focus on rock data. It's one of the nice things about working in the northeastern U.S. and southeastern Canada as compared to New Madrid is that most of the stations are sited on rock, which removes some of the complications of site, which helps a little. Next. So with that data, here's just a typical plot of how the events appear to attenuate with distance. This shows Fourier amplitudes at 4 different frequencies for earthquakes that are magnitude 3.5 plus or minus a quarter unit. And the dark dots are the plus side of the 3.5 and the light dots are the minus side of the 3.5. And shown strictly for reference are 2 reference attenuation models, both of which are bilinear, meaning that they have one hinge representing a transition from direct wave spreading to LG spreading, and that hinge has been put at 60 kilometers. And the main point of these is to show the effect of different geometric spreading. The blue line has a geometric spreading of r to the minus 1.3 and close, and the red line is a 1 over r model. They're both assumed to be r to the minus a half with some standard Q model beyond that. There's also a dashed line there for a higher value of stress drop. So 2 values of stress drop are shown, 200 bars and 600 bars. At low frequencies, it doesn't matter what stress drop you use because it's the moment that controls the amplitude level of the curves, the combination of moment and geometric spreading. Whereas at the higher frequencies, then there's also the value of stress drop comes into play. Next. So as we move up in magnitude, the data gets sparser, and we see less and less when we compare the data with the curve. This is showing magnitude 4.7, and the reason I put this one on is this is actually for a single event, the Rivière-du-Loup earthquake of 2005, and this is actually the only decent-sized event in the entire Eastern North American database in which we have a pretty good distribution of data over a wide range of distances, going from all the way from about 20 kilometers out. And those same 2 reference attenuation models are plotted on there. And one of the things that you see on this graph, which you also could have seen on the previous graph, is that at the low frequencies, the top 2 graphs, the attenuation definitely appears to be steeper than 1 over r in the first 60 kilometers. But when you look at the higher frequencies, it's not so clear. So if I move on to the next slide, one of the things that I noticed scanning through event plots like this is that the anelastic attenuation is not the same for every single event, and it's the one parameter that we can determine fairly easily. So I thought, well, okay, why don't we look at the anelastic attenuation for each event and remove that and see what's left to see if we can say anything about geometric spreading. So I estimated the Q for every event just using the data beyond 150 kilometers, 150 to 500 kilometers. And the blue dots there are showing over the whole database what the average event Q is. And the error bars represent a standard deviation, basically showing how much it can vary, the apparent Q, from one event to another. And then the red and the blue lines show typical conventional Q models determined by regression analyses for Q in the east. The red line is my 2004 estimate, and the blue line is the Boatwright and Seekins 2011. And so you can see that the average Q kind of lies somewhere in between the two. So if we go to the next one. So then what I did was I removed that Q and the r to the minus a half spreading from all of the data, not just beyond 150 kilometers, but all the way into the closest observations we had, so that we could look at the residual. If we take out the known Q for each event and r to the minus a half spreading, what attenuation, what apparent attenuation is left? And so we know that the residuals are going to be 0 from 150 to 500 kilometers because we've kind of done that by definition. And so that's indeed what you see here. But then the interesting thing is, as we go back from the source, if we had just assumed that the r to the minus a half goes all the way back into the source, we can see what the deviation from that model is. And what we expect to see is a positive residual as we get inside about 100 kilometers and move to direct wave spreading. We expect to see a positive residual. What we see is that, yes, we do see that, but the amount of the positive residual is highly dependent on frequency. So it appears that there are frequency-dependent effects that are left in the apparent geometric spreading after we've removed the Q effect. Next. So we could parameterize that in a number of ways. We don't really know what's going on. But if we want to just flatten those residuals and come up with a model that takes the trends out, a simple model that does that would be to say, assume that it's a bilinear model, but that the transition from direct wave spreading, steep spreading, to LG is a function of frequency. And so we can get rid of most of the residuals if we assume that the transition distance is 70 kilometers at low frequencies and then transitions to 30 kilometers at high frequencies. Next. And so this is just a few plots to show what that model would look like, and I'll just kind of scan through those fairly quickly. So this is for that Rivière de Leux earthquake. The red line is if we assume a bilinear model with r to the minus 1.3 transitioning to LG spreading at a transition point that depends on the frequency. And so, you know, it looks quite reasonable. And then by comparison, in these plots, I'm just showing the dashed blue line is the Boatwright and Seekins attenuation, which is also bilinear but has 1 over r spreading. And I'm just showing that for a nominal stress drop of 200 bars, whereas the red lines is for the best fit stress drop. Next. And so this is just a similar plot for the magnitude 5 Val de Bois earthquake in 2010. You can see sometimes the two different attenuation models give almost the same answer at regional distances, and sometimes there's a bit of an offset. Next. And here's for the Saguenay earthquake going back to 1988, where we have considerably sparser data. And so if I go on to the next one, then we can look at what does the source look like for those different attenuation, or for those different earthquakes using that bilinear attenuation model. And this is the source spectrum that you get for the best earthquake, the Rivière de Leux. And you can see that if you take the amplitudes all the way back to the source, you actually get a very nice Brune-type spectrum. This is a stress drop of 170 bars. There's a bit of a shift there in that when you take the amplitudes back to the source, there's no guarantee that you will match the known moment of the event from moment tensor solutions. And so I shift the spectrum so that the moment and the stress drop go together so that you get the correct shape. And so there's always a little bit of a shift there. So that's what the Rivière de Leux spectrum looks like. Next. I'll just scan these quickly. That's the magnitude 5 Val de Bois spectrum. And then finally, Yep, that's the Saguenay spectrum. And you see, by the time you get to Saguenay, 1988, the data were pretty ratty. And so you get a ratty-looking source spectrum and a suggestion that maybe it has a fairly high kappa or high-frequency roll-off. And that sort of raised an interesting question that I show briefly on the next slide. And that's the trade-off between stress and kappa. You can kind of imagine that if you took two quite different source models, the stress drop there is different in those two plots or those two lines by a factor of 2, but they have different kappa values, and add in some variability that it might be quite difficult to tell the difference between those two. And next one. There's another interesting thing to note, and that is that if that transition to LG spreading really is frequency dependent, that introduces a change in the shape of the source spectrum by the time you get to regional distances. And in particular, if we start with a Brune spectrum, the red line at the top, that's 250 bars, and we attenuate it with a frequency-dependent transition distance, we get the solid red line at the bottom, which looks like it has two corner frequencies. And we would infer from that red line at the bottom, if we assumed that if we didn't know about a frequency dependence in the shape, we might assume that it had a higher stress drop, about 600 bars, and a double corner. Next. This is my last slide. So in conclusion, this is an attenuation model that one can come up with that actually fits the data, but it's strictly an observational phenomenological model. We don't know whether, what this really means. What I conclude is that there are just so many trade-offs between the source and the attenuation parameters that those act together with the sparseness of the data to create very large uncertainties in what the values of source parameters actually are. And one of the consequences of that is that the stress and the geometric spreading at close distances are really closely intertwined, and we can't actually determine the stress drop uniquely for most events in the East. Thank you.
Okay, do we have any questions? Yes, one over here.
The Q is the parameter we probably know the best. The residual geometric spreading is not actually sensitive to Q. Stress drop is sensitive to Q if you only have regional observations, but it's even more sensitive to geometric spreading. So stress drop is actually more sensitive to geometric spreading from regional observations than it is to Q.
Okay, no further questions. Thank you, Gail. Okay, we're now moving on to a talk by Rob Graves, calibration of a 1D crustal velocity and Q model for ground motion simulations in central and eastern U.S.
Okay, thank you, Bill. So this is work that has been done as part of the PEER NGA East project, which is developing ground motion prediction equations. Okay, so this is PEER NGA East work. It was funding support provided by the NRC. So the objective in this, it's a very broad brush. We'd like to develop and calibrate a 1D velocity model and Q model for central and eastern U.S. that we can use in full waveform simulations. The approach here is to model low-frequency ground motions for Mount Carmel and Mineral Virginia earthquake using an FK approach. The starting model is based or extracted from a 3D velocity structure that was recently published in BSSA by Ramirez-Guzman. Now, the assumptions and limitations, the bandwidth here is 1 hertz and lower. We're looking at generic rock site conditions, surface velocity 2,200 meters per second. The earthquakes that are in the modeling are simple point sources. In the region, central and eastern U.S., although Mississippi embayment and Gulf Coast regions are not appropriate for this 1D model. Okay, so let's start with Mount Carmel, 2008. This earthquake is almost or strike slip mechanism. There's a moment tensor solutions. Actually, a couple of them have been published. Magnitude is about 5.2. Depth about 14 kilometers. The mechanism that is used in this study is from Yang et al., so it has a slight dip, a little bit of oblique slip. Since I'm calculating full waveform synthetics, I have to assume a slip rate function. I'm using a Brun-type pulse, and the corner frequency here is derived or taken from a study by Hartzell and Mendoza, 0.89 hertz. Now, the sites which I'm primarily trying to model are these green circles. The red triangles are the Mississippi embayment sites. This bold line here delineates the embayment. Just for reference, these circles here, this is 500 kilometers epicentral distance, and this is 1,000 kilometers epicentral distance. So we're going out to quite far distance. Okay, in terms of developing the initial model, the 3D velocity model, CUS version 1.3, this is just coming out in BSSA. The region that is covered by that model is shown by this blue rectangle. So you can see it encompasses a number of our sites, but many of the sites are outside of that region. So what we've done, though, is we've just kind of blindly extracted 1D profiles at all these sites to use as our starting velocity structure. So that's shown here. So this is the shear wave velocity is a function of depth for all of those sites. There's about 65 sites total there. You can see they're actually fairly similar with some variations in the near surface and some down near the MOHO. I constructed an average profile, which is shown by this red line here. The surface velocity is constrained at 2,200 meters per second, and then the MOHO depth is at 40 kilometers. You can see there's a slight gradient above the MOHO in this model, constant velocity below the MOHO in this model. And just for reference, the green model shown here is a model presented a number of years ago by Wang and Herman. So this model is similar, but so it shows some more detail. Now, the initial model has in the mid to lower crust, has a Q for shear velocity or shear waves at 700. I'll show some results of that, but then also a model where I bumped it up to 5,000. 5,000, it's pretty high. This improves the fit to the motions at further distance. Okay, so here's some example of waveforms. So on the left, these three panels, this is tangential, radial, and vertical. These are observed ground velocity, filtered at 1 hertz and lower, going from 0 out to nearly 1,000 kilometers. The red lines on here are roughly P wave arrival and S wave arrival. The red lines are the same on each one of these panels. On the right are the simulated motions, and for each of these same stations, this is for the Mount Carmel earthquake. So you can see that, in general, the timing of the main arrivals is matched reasonably well, but clearly we're missing a lot of the complexity, particularly as we get out here further in distance in the simulated motions. And this is something that is not included in the model. I would attribute a lot of that to crustal scattering. Okay, so now here's a plot looking at the attenuation of ground motion with distance. So we're looking at the ground motion parameter spectral acceleration at 2 seconds. This is the geometric mean of the two horizontal components. And this is plotted as a function of closest distance. The symbols that are plotted on here, the gold symbols, are recorded non-embayment. So those correspond to all those green circles I showed on the earlier sites. The magenta squares are the embayment sites, and you can see those are very clearly elevated in amplitude out here. Let me skip to the black line here is a ground motion prediction equation, Atkinson and Bohr, 2006. This is rock site relation with plus and minus 1 standard deviation. And then the crosses are the simulations, the simulated values where I've extracted the spectral acceleration from those waveforms. Okay, now there's some characteristics here in terms of the data where you can see, for example, this flattening out here around 100 kilometers. It looks like that is a feature in the data. It's predicted by the models. The simulations actually do a reasonably good job in terms of matching the level of ground motions. Now this is for the initial model of the Q of 700. You can see if I bump that up, the simulated sites out here do a little bit better in terms of fitting the attenuation at those further distances. Okay, now let's look at this in terms of residuals. So this is just taking all those data. The red are the non-abatement sites, so this is the residual observed minus the simulated. The crosses here are the abatement sites, and this is for the 2-second spectral acceleration. And as a function of distance across this distance band, this is the misfit parameter. It's actually fairly close to 0. Obviously, a lot of scatter. For the abatement sites, obviously, we underpredict those sites. Looking at a slightly longer period, this is for 5-second period, we see again that across the distance band, the similar level of fit with a very small median bias. So in general, this model is doing pretty well in terms of matching the distance attenuation. We now look at this in terms of a map view. 2 seconds spectral acceleration is shown on the left, 5 seconds is shown on the right. Some very clear trends, obviously the Mississippi abatement and also these Gulf Coast sites show very strong underprediction, so those are excluded from this model. In general, at 5 seconds period, the match is pretty good across all the distances. At 2 second spectral acceleration, we see some high sites and some low sites as well, and I attribute this to unmodeled site response at those particular locations. Okay, now moving on to Mineral, Virginia. So this is a slightly larger event. Magnitude 5.65 is what I used here. That's based on the work Bob Herman had done. 6 kilometers in depth. Primarily, it's a thrust event. Again, the same kind of color scheme here. We're excluding these sites in the abatement. Those are at quite a far distance. Notice, though, that I don't necessarily expect this model developed for this region to be applicable, but we're kind of just doing this as a leap of faith. The slip rate function, slightly lower corner frequency, and I derived this just by scaling as a ratio of the moments relative to Mount Carmel. So let's see how this does. As been mentioned in previous talks, not a lot of data in close. Well, we see a similar trend in terms of the simulations kind of going through the mean of the observations. Again, here's the ground motion prediction equation, Atkinson and Bohr, maybe a little bit low for this event. And again, there's not a whole lot of data, but there certainly is a suggestion or a hint of this flattening, which appears to be reproduced in the simulations as well as the GMPE. Okay, residual plots shown again here for 2 seconds on the top panel and for 5 seconds on the bottom panel. In general, the match is pretty good, except there is a slight trend at further distance, both at 2 seconds and at 5 seconds of over-prediction. Our simulations are over-predicting, and that may be due to just the regional differences in the velocity model. If we look at this in map view, there's a very striking pattern that is apparent, and that is this kind of northeast to southwest change in the character of the residuals. And it's very strong here at 2 seconds period, where the motions in the northeast are underpredicted and the motions to the southwest are overpredicted. There's a hint of that here at 5 seconds. This could be easily attributed to source directivity if the event located here ruptured towards the northeast, which has been proposed and I think is fairly well documented. That would tend to increase those motions and decrease these motions. Our point source model obviously does not capture that. There is some other interesting kind of feature here up in the northeast at 5 seconds period. I'm not sure exactly what's going on with that, but that may indicate some regional variations as well. Very quick word about intensity. I'm looking at 2-second spectral acceleration. The reason why is because this is where I think I might have some confidence in doing the ground motion modeling. One idea was to predict intensities from this, and there are some recent ground motion intensity conversion relations that utilize 2-second spectral acceleration. This allows comparison with a much broader data set, the Did You Feel It data set, for example. I won't go through the details here, but let me just say the main conclusions. The 2011 relation, Dangu and Kramer, does well in close and for larger MMIs. The Atkinson and Kaka relation does better for further distances or lower MMIs. And so this is a feature that maybe needs to be looked at a little bit more in terms of these relations. Okay, summary. Developed the model based on the average of this 3D velocity model by Ramirez-Guzman. The initial model works well for the long periods for Mount Carmel out to about 400 kilometers, including the flattening, but underpredicts the more distant sites, and that can be corrected by increasing the Q. Taking that model and applying it to mineral seems to work pretty well, even out to about 1,000 kilometers, although we are not capturing this northeast to southwest bias, which is probably related to directivity. And the model does exclude the region, or does not include the regions of the Mississippi embayment and Gulf Coast. And that's it. Thank you.
Thank you, Rob. Do we have any questions? Yeah, Bob.
Okay, I haven't done that. I'll take a look at it. Yeah, I realized that when you made your talk earlier, and I was thinking about that, and I thought, could I redo this in the 45 minutes before my talk? But, so I have something to work on over Christmas break. Yeah.
Okay, thank you, Rob. So next up, we have the man of the hour, Rasul Anushapur, who has been busy this week presenting papers on the behalf of his colleagues at the NRC, who perhaps didn't get permission to travel here, which has been a headache for all of us federal employees. So Rasul is now going to present the talk, Understanding Earthquake Process in the Central and Eastern U.S. and its Implications for Nuclear Reactor Safety.
Thank you, Bill. I'm actually going to mostly read from the notes, so forgive me. I can't memorize anymore as I used to when I was younger. And also, this is not my area, so if there are questions, I can see some familiar faces in the audience, so you're welcome to help me out if there are questions. Okay. So in this presentation, first I will briefly discuss the role and responsibilities of the Nuclear Regulatory Commission. I will also give an overview of the application process for new reactor license application with respect to seismic hazard. And I will then discuss how these new reactor applications are reviewed by NRC and how an in-depth understanding of earthquake process in the central and eastern U.S. play an important part of this review. Finally, I will discuss opportunity for the scientific community and the public to get involved. The NRC's mission is to license and regulate the nation's civilian use of byproduct, source, and special nuclear material in order to ensure adequate protection of public health and safety, to promote the common defense and security, and to protect the environment. And NRC's regulatory mission covers three main areas: reactors, materials, and waste. And on this map, this is the large historical earthquakes, and these triangles show the location of currently operating nuclear power plants. And as you can see, most of the plants are on the central, east of Rockies in central and eastern U.S. So that's why it's important that we understand the process in this region. And this one shows the central and eastern United States, and with the earthquakes from the central and eastern U.S. Project catalog, which are magnitudes greater than 3. And the green, again, the green triangles show the existing nuclear power plants, and the stars show the application for this new nuclear power plants that they have been submitted to NRC. Next. Okay. As part of the submitting an application, applicants need to conduct seismic hazard analysis following federal regulation and NRC regulatory guidance. So applicants need to determine the ground motion response spectra for the proposed sites and establish the design basis safe shutdown earthquake ground motion. It's called SSE. And the ground motion response spectra is the review level ground motion for the design of the nuclear power plant sites. And the results of the applicant's analysis are submitted as part of a final safety analysis report. Next one, please. And NRC extensively reviews the seismic hazard analysis results contained in the applicant's final safety analysis report to make sure that it meets all of the regulatory requirements and scientific accuracy. As part of the review process, the NRC interfaces with the applicants to gather additional information. NRC also conducts confirmatory analysis and calculations. The results of NRC review is documented in a safety evaluation report. Okay. This slide summarizes the key elements of seismic review for new reactor applications: seismic source characterization and development of ground motion prediction equations and probabilistic seismic hazard analysis, and a site response analysis to incorporate the effects of local geology and calculations to determine the ground motion response spectra. Next, please. For potential sites located in the central and eastern U.S. states, there is an NRC-endorsed seismic source model that applicants must use as a starting point. This will be discussed in more detail in the next few slides. And for potential sites in the western United States, there are no NRC-endorsed starting seismic source models. Each applicant needs to develop their own seismic source model following methodologies which are acceptable to NRC. Next, please. The Central Eastern U.S. Seismic Source Model published in January 2012 and is the result of a joint effort by NRC, Department of Energy, and Electric Power Research Institute. The model is a regional model applicable to any Central Eastern U.S. sites, and it incorporates recent scientific information on seismic source capable of producing earthquakes in the Central and Eastern U.S. The spatial distribution of future earthquakes is defined by the geometry of 3 different source zone types. And these 3 different are sources of repeated large magnitude earthquakes, they call it RLMEs, maximum earthquake source zones, and seismotectonic zones. In all cases, uncertainties in these seismic source model parameters are captured by varying alternatives. Okay. This is RLME sources are the location of repeated large magnitude, like New Madrid, greater than magnitude 6.5, earthquakes in the historical or paleo earthquake records. For example, the New Madrid seismic source zone and Charleston seismic zone source. The two alternative approaches to defining the spatial distribution of earthquakes outside the RLME sources are source boundaries defined only on the basis of maximum magnitude differences, and then the source zones defined by their different seismotectonic characteristics. These source zones types are described in the next couple of slides. This figure depicts the alternative representative of MX sources. The maximum zone branches consider only this parameter in defining the alternative models. I don't understand this very well myself, but I think the regions for MX are divided into, there are two different alternatives, and they are divided in two different zones each, which one is called the Mesozoic and younger extension, and non-Mesozoic and younger extension. And I believe one is called narrow and one is called wide. So these are the two different models for MX. Next. And the third alternative is, this figure shows one of the four alternative seismotectonic source zones configurations. The seismotectonic zones are defined based on the regional differences in characteristics such as recurrence rate, Mmax, and future earthquake characteristics. The recurrence rate within the Mmax and seismotectonic source zones are allowed to vary according to the smoothing of observed seismicity. Next, please. The NRC has endorsed the new Central Eastern U.S. seismic source model as an acceptable starting model for nuclear power plants, PSHAs. However, since it is a regional model, local refinements may be necessary to accommodate local information. For new reactor applications, studies are required to determine if local updates are needed. Potential area for local updates include the Eastern Tennessee seismic zone, the Central Virginia seismic zone, and Oklahoma and Arkansas. Updates to seismic source geometries, seismicity rates, and maximum magnitude may be needed. Now, opportunities for the involvement of the geoscience community. So, awareness of science needs in the area of nuclear safety, development of new and updated seismic source characterization in the Central Eastern U.S., involvement in the NRC regulatory processes and the aspects of the geoscience review through public meetings, and development of workforce knowledgeable about seismic safety issues as applied to nuclear power plants. Next. Avenues of involvement, direct participation. Oh, I need some water. Oh, here. Oh. Must be the coffee I had. Participation by public in technical meetings between NRC staff and the applicants in person or via teleconferences. These meetings are announced 10 days prior to meeting date. NRC staff relies heavily on current research activities to get informed, which requires interfacing with researchers. Indirect participation, focusing on science needs and conducting new research related to seismic source characterization anywhere in the U.S., especially in the central and eastern U.S., by accessing technical documents at NRC websites to get informed about relevant technical issues. And I guess you can read them. Bringing geoscience and public policy issues together in classroom activities, And let's see, what's the next? Yeah, and these are resources, NRC website, and also documents related to the, is there? Let's see, there was one for this Central and Eastern. Yeah, there is information on the Central and Eastern, I guess, Eastern U.S. seismic source model is available at the website www.centraleasternus-ssc.com. It is about 3,000 pages. Thank you.
Okay, thank you, Russell. Does anyone have a comment or a question to pass along? Okay, thank you again. If not, let's move on to the next talk, which is going to be presented by Etrier Gauche, The Dynamics of Eastern North America, Intraplate Strain and Stress.
Okay, so thanks for coming on the Friday afternoon. All right, so most of you know that there was a magnitude 5.7 earthquake in Virginia in August 2011. Now, if you look at the seismicity map of the world, you see that most of the major earthquakes take place along active plate boundaries. However, Virginia does not sit on an active plate boundary. In fact, it is part of the passive continental margin. Now, here is a figure from Bolin et al. GRL paper that shows seismicity in the passive continental margins all over the world. So you see that there are quite a few magnitude 6 and above earthquakes, and also a few magnitude 7 earthquakes. So in fact, passive continental margins are not passive at all. And coming back to North America, these are some of the recent major earthquakes that have taken place in this region. For example, the 1933 Baffin Bay earthquake with magnitude of 7.4, 1929 Grand Banks 7.2 magnitude, and of course the New Madrid earthquake in 1812 with a magnitude of 7.7. So the question is, what's causing these intraplate earthquakes? In fact, one of the basic tenets of plate tectonics is that the plate interiors are rigid and non-deforming. So why are we having these earthquakes in the middle of the plate? Well, the truth is there is no comprehensive model to explain these earthquakes. But there is a consensus that these earthquakes happen due to reactivation of old pre-existing faults. Now, there are several theories why these faults can get reactivated, and these are large-scale plate tectonic effects taking place over longer time scales. It could be due to glacial-isostatic adjustment, which is especially true in the case of North America. Could be due to localized stresses, and also could be due to dynamic topography. Now, in this talk, I'm just going to focus on the tectonic effects. So basically, I'm just going to show that how much of these earthquakes can be explained just from a tectonic point of view. Okay, so the way we approach this problem is to solve a set of three-dimensional force balance equations using a global finite element model that couples lithosphere and mantle convection. And this is a procedure that we have used in some of our recent papers. So what goes into the model is a density and the viscosity structure. So the density structure comes from two sources. In the lithosphere, it's from the Crust 2.0 data set, and and in the oceanic lithosphere, it's from it's the cooling from based on seafloor ages. And in the mantle, the density structure is from tomography and history of subduction. And we also incorporate radial and lateral viscosity variations in the model. The lateral viscosity variations come from stiff continental cratons, old oceanic lithospheres, which is also stiff, as well as weak plate boundaries. And what we are predicting are deviatoric stresses, strain rates, and velocities. Okay, so just to emphasize the point that it is a coupled model which has a lithosphere component and a mantle component. And here I'm just showing, without going into detail, the stress response, the deviatoric stress response, just from the lithosphere component alone. So these are the predicted deviatoric stress axes. Black means they are in compression, and red and white means they are in extension. So here I also plot the focal mechanism of the Virginia quake, and you can see that the contribution from the lithosphere alone does not satisfy the mechanism of the Virginia quake. And then we also have the mantle contribution. So here I'm showing the mantle tractions at the base of the lithosphere from a mantle convection model. This is a fully dynamic model, and we do not impose any kind of a priori surface velocity boundary condition. So the signal is dominated by this large downwelling in eastern North America, which is due to the sinking of the Farallon slab. And this is basically a very big signal, and it has a lot of implications on the tectonics in this region. Okay, so here is the input lithosphere viscosity structure. So the plate interiors have a constant viscosity of 10 to the power 23 pascal second, while the plate boundaries have lower viscosities. And based on this structure, here are the predicted velocities. So in red are the velocity vectors from our model in the North American plate with respect to a fixed Pacific plate. And in blue are the GPS vectors from the Creamer et al. Study. So we see that our predicted velocities are very consistent with these kinematic velocities. And we also predict the Pacific North American pole of rotation, which is indicated by this red star. And this is also very consistent with the kinematic pole indicated by blue star from the Marvel model. Okay, so these are the predicted strain rates from our model. And what's important to note here is that the intraplate areas are also deforming at a small rate. So the strain rates are not zero in the intraplate areas. They have a small value of about 5 times 10 to the power minus 9 per year. Okay, so these are all global models, but I'm just going to focus in the next few slides on this part of Eastern North America. So I'm going to show you the seismicity in this region and how much of that seismicity can be explained from these stresses from tectonic sources. So we start with our initial model, which has a constant intraplate viscosity. And we basically test 3 different cases. So the first case is the simple case with a constant viscosity in the intraplate regions. In the second case, we introduce a strong cratonic region with a higher viscosity of 10 to the power 24 pascal second. And in the third case, in addition to the weak plate boundaries and the strong craton, we also add a stiff oceanic lithosphere, old oceanic lithosphere. So here are the predicted deviatoric stresses from the 3 cases. So in the first case, with the constant intraplate viscosity, we see that the trend is mostly almost east-west. And here again, I plot the mechanism of the Virginia quake. And also to reiterate, the black axis are compressional, and the red and the white are extensional. So for the second case, when we introduce strong cratons, we see that the stress axes undergo a dramatic change in orientation from an east-west to an almost northeast-southwest orientation. And for the third case, when we introduce old oceanic lithosphere, strong oceanic lithosphere, the stress axes within the interior stay more or less the same, but in the eastern seaboard, the orientation change in a more northwest-southeast direction. So I would like to mention here that these change in orientation of the stress axis that have been noted, that have been observed and noted earlier by Zobak and Zobak in 1980 science paper. And it is pretty exciting that just by using a simple intraplate viscosity model, we can actually predict these change in orientation of stresses. Okay, so if we just focus on the region of the Virginia quake, we see that for the first case, our stresses cannot explain the mechanism of the Virginia earthquake. For the second case, with a stiff continental interior, the stresses are, the angular misfit is a little less, but still we cannot actually explain the mechanism well. But in the third case, when we introduce the strong oceanic lithosphere, we see that our predicted compressional axes are quite consistent with the pressure axis of the Virginia earthquake. And in the next slide, I show the seismicity in the eastern U.S. compiled from different sources. And here I have plotted the deviatoric stress axis from the third model, which has intraplate viscosities due to strong Quaternary lithosphere as well as old oceanic lithosphere. So we see that we can match the mechanisms of most of these earthquakes pretty well. And so basically the major conclusion is that in this region where people argue that the GIA effect can play a very important role, we can actually satisfy most of these earthquakes just from tectonic sources. So that's the main point here. Okay, and so also this one of the questions that we wanted to ask is it possible to isolate the tectonic effects from the GIA effects in the GPS signal north of the hinge line in North America? So here is the predicted velocities of our model with respect to a stable plate interior. So there is occurring about 1 millimeter of shortening in this area. And here I show the different ice sheet, the predicted velocities from different ice sheet models from the Sella et al. GRL paper. So you see the pattern of these velocities is radial, and which is very different from this tectonic effect, which is more or less an east-west effect. So the answer to the question is yes, it is. We think that it is possible to actually deconvolve the signals, the two signals, the tectonic and the GIA signals from the GPS velocities. Okay, so here is the summary. Earthquake mechanisms are quite consistent from our predicted stresses from tectonic sources. Intraplate effective viscosity variations can explain the intraplate stress orientations and focal mechanisms. And we can predict the transition in orientation of stresses in the Eastern North America from eastern seaboard to the margin to the interior of the continent, as has been seen by Zobak and Zobak. And finally, it is possible to actually isolate the tectonic signal from the GIA signal in the GPS, because both of them have a very different signals. So, thank you.
Thank you. We have time for a question or two. Okay, thank you very much. We'll move on to the next talk. And this is going to be presented by Beatrice Magnani, Distribution of Long-Term Quaternary Deformation and Correlation with Pre-Existing Tectonic Structures in the Central U.S.
Thank you. Thank you. Well, thank you for braving the 5 o'clock on Friday. thought I needed to bring a bottle of wine to have you guys here. Okay, here we go. Can I drive? Okay, good. Well, thank you. Okay, by now, you know everything about the New Madrid seismic zone, so I won't bore you with all the seismicity details. I'll tell you just that. Do I have a pointer or? Yes, I do. So I won't bore you with the seismicity details. I'll just say that it was the location of 3 main large earthquakes in 1811, 1812. It produces 200 earthquakes a year of small magnitude, and has a return time of 500 years as detected from the paleoseismological record. So I thought the topography of this region might fool you. This region has been the location of a series of very impressive tectonic events, and they include the assembly and the amalgamation of the supercontinent Rodinia, and all the boundaries that I'm going to show you are from the latest paper by Bill Thomas. And so the boundary of the Grenville front, that's the guest location. And then the breakup of the supercontinent and the opening of the Iapetus Ocean. And in green, you see the formation of and the structure of the Reelfoot Rift and the location of the Alabama-Oklahoma transform that marks the southern margin of the Proterozoic lithosphere, Laurentian lithosphere. And then again, the amalgamation of yet another supercontinent, Pangaea. And that is the front of the Ouachita Fault and Thrust Belt. Now, the New Madrid seismic zone is located nested within one of this old structure. And one of the, if we look at the crustal structure under the New Madrid seismic zone, we see that this interesting tectonic history of the formation actually has left a mark in the crustal structure. In fact, this is a series of wide-angle refraction profiles that were shot in the 1980s by the USGS group. And this is the southernmost profile that shows a pretty interesting structure in the lower crust with a fast layer that has been interpreted as an altered lower crust with the velocities greater than 7. This could be likened to a 7XX layer. And has been interpreted as a mafic intrusion or a gabbro. And so has been interpreted as a residual material left behind by the rift pillow and associated with the rifting process. Now, because this structure seems to be associated with the location of the seismicity, has also been invoked to be necessary to the seismicity we observe today. And so if we review some of the deformation driving mechanism in this region, we see that they need this predisposing crustal structure, which is the anomalous presence of this high velocity layer located under the New Madrid seismic zone. And then we need an additional perturbation of the stress field, which we call the Holocene trigger, which could be the sinking Farallon slab, or as we heard, the retreat of the glacier, so a sort of an elastic rebound, or a Holocene change in plate motion. But whatever the mechanism, any mechanism that invokes these, the presence of the rift pillow as a key feature for localizing the strain in this region predicts that the deformation is only located where this structure is. So perhaps one of the questions that we can ask is how unique this structure is. And to look at that, I actually pulled up a very old profile by Braille, 1989. And this shows the crustal structure of the mid-continent along the 37 north latitude. That is a compilation of all the available data existing at that time, and it hasn't changed that much since. And I don't know if you noticed, if you attended the talk on Monday by Vera and the group in Colorado. She showed a very similar profile now from the TA ray. Anyway, so this crustal profile shows the presence of a very interesting feature, again, the 7XX layer, a pretty thick layer, about 20 kilometers thick, sitting at the base of the crust, with velocity, P-wave velocity greater than 7. And it looks like it's a pretty ubiquitous feature of the granite rhyolite zone. And as you see, this is this is now the real this is the Mississippi embayment. It looks like the rift pillow seems to sit on top of this ubiquitous structure, as if is been emplaced and is thickening a pre-existing structure. Now, to test then if this structure is unique or is not, I'm going to show you some of the result of a 950 kilometers long profile that we acquired along the Mississippi River. I'm not going to show you 950 kilometers long, high resolution data. We're going to be here till tomorrow, but I'm going to show you just short highlights of it. And I want to show it to you because this profile is both inside and outside the region of the rift below. And because also there is a mounting evidence, not just from this profile, but also from a lot of paleoseismological and high-resolution data in the embayment, that the long-term deformation in the embayment has been accommodated not just in the region where the rift pillow is located, but also outside. So what we did, we went along the river for 3 summers, and we drifted backwards on a barge. And if you've never spent several weeks in the summer along the river, I'll assure you it gives you a new perspective on Mark Twain. And so we collected this 950 kilometers of high resolution. We've imaged the unconsolidated sediments all the way down from the Quaternary alluvium to the top of the Paleozoic units. And I'm going to start showing you one line up here, one line up here, one here, and then we're going to go all the way down to the Alabama-Oklahoma transform. Okay, let's look at the New Madrid seismic zone. And we're going to look at this slide that goes right across the southern arm of the seismicity. And this southern arm of the seismicity has been called with any number of names, you name it. I'm going to call it the axial fault because that's how Zobach and Hamilton called it in 1978. And this fault we know from focal mechanism, and this is from a thesis of Steve Horton at SIRI, but also corroborates the data by Bob Herman and Jack Hammond, shows that this fault is practically vertical. It strikes north 45 east, and it's almost purely strike slip, as a rake of 178 degrees. So almost purely dextrose strike slip. So when we shot the line across it, we noticed that, so you see these are the Paleozoic sediments, green is Cretaceous, everything else is tertiary, and then in yellow is the Quaternary. What you see is that we found 2 faults, not just one, or 2 main areas of deformation, and one is deforming, very consistently all the packages all the way up to the base of the Quaternary. And you see that the deformation decreases with as the sediments become younger, suggesting that this deformation has been cumulative with time. And also we found another fault, and to the west of this main zone of deformation. And what was most striking to us was that we found a substantial amount of vertical displacement at the base of the Quaternary alluvium. So we found 25 meters of vertical displacement across here, and another 23 meters of vertical displacement across here, which we found was quite striking, considering that the fault at depth moves almost completely strike slip. So we tried to map the faults using all the existing data. And this is the seismicity. So we used all the data existing from the USGS. This is the high-resolution data that have been collected throughout, the past 20 years by the USGS. And this is an integration of our data along the river and the USGS high-resolution profiles to try to map the surface expression of these faults, or at least the expression in the unconsolidated sediments. And what you're seeing here in green is the seismicity. This is the relocated seismicity by Heather using TomoDD techniques. So this is actually just the catalog from 95 till 2011. And so it's a pretty accurate representation of the seismicity at depth. And so as we try to integrate what we see along the river and what we see on those profiles, this is what we found. We traced very clearly the 2 strike slip system in the northern portion of the New Madrid seismic zone, The real foot thrust is very clearly traceable along every profile. And then the cottonwood growth fault is a very linear feature to the south. And we can, convince ourselves that this is, either a system that connects to the axial fault or not. When we try to connect, then, instead to map the northeast part, oh my God, this is really, I need to speed up, then it becomes much more complicated and suggests that this is a flower structure, and that there is a lot of vertical deformation that occurs here that doesn't seem to be represented by the fault at depth, which perhaps suggests that we should be careful about interpreting the GPS data we collect at the surface when we try to link them to the seismicity at depth. Okay, so what happens at depth? Here I'm plotting the seismicity that shows that most of the seismicity is actually beneath the axial fault, and this is the Cottonwood Grove fault, which is to the east. And we can convince again that these are two separate structures, separated by 6 kilometers, one active and one seismogenic, one not, or maybe they are one single structure, and two parts of a flower structure. Okay, now we move south, and now we are outside the New Madrid seismic zone, and we see a very similar story. Similar structure, another fault, deformed all the way up to the base of the Quaternary. Again, greater deformation in the older strata than in the younger strata. And then we move again even more south. We're now 100 kilometers south of the New Madrid seismic zone along the Miemen-Shelby fault. Similar structure, similar deformation, very young. This is 25 meters of elevation across this crest. And we follow this fault actually along several intersections of the river, and we've been able to trace it. And we know we've imaged it for 45 kilometers, and we know that this is a fault that can generate substantial earthquakes. Earthquakes that are comparable to the New Madrid, magnitude that are comparable to the New Madrid seismic zone. And so we've actually, and are capable of liquefaction as well as the New Madrid seismic zone faults have been able to. So I'm going to show you a very high resolution profile that we shot here. And now this is a different technique. This is chirp data. What you see here, this is the bottom of the river. This is the first water bottom multiple. So don't mind anything below here. And this is the top of the Eocene. And this is the Eocene has been very deformed, probably by liquefaction of the Memphis sand. Okay, we're now moving. We looked at these 3 areas. And I'm going to show you the last line right across the Alabama-Oklahoma transform. And this is what we see. A very, very well-developed fault that displaces the top of the Paleozoic, Cretaceous, all the way up to the base of the Quaternary. And this fault is located next to 2 liquefaction fields as identified by Randy Cox that show 3 major venting episodes in the last 7,000 years. And the size of the liquefaction suggests a local seismic source, not something that is associated with the farther seismic sources. And when we shot the seismic profile right next to that, that's what we found. Now that Eocene that we saw well stratified to the north now is completely deformed here. And we interpreted, because this profile is right next to those liquefaction sites, we interpret this as liquefaction at the edge of Laurentia. So maybe one of the most striking conclusions of our imaging was that along 950 kilometers of profile, we find this seismicity, this quaternary deformation associated with the edge of the real foot rift and the Alabama-Oklahoma transform, but nothing was associated with the Ouachita front. So the Ouachita front has not been reactivated in the Quaternary. So maybe a question that we should ask is, what's the difference between the real foot rift, the Alabama-Oklahoma transform, and the Ouachita collision? And the answer is that I don't know. But one of the possible answer is that this, like the Alabama-Oklahoma transform, is a through-going as a crustal structure that involves the modification of the mantle and the lithosphere, whereas the Ouachita front is something that has been defined as a soft collision without much of the deformation of the mantle and much involvement of the mantle, suggesting that only those structures that involve the mantle are now playing a role in the location of the quaternary seismicity. And so, my conclusions are that the present seismicity in the Mississippi embayment does not reflect where the quaternary deformation has been accommodated in the long term, and the deformation is not ubiquitously distributed. It's very localized along few distinct faults. and that these faults exhibit a long history of deformation, and also these faults are located along pre-existing structure that are associated with the early history of the Laurentian continent. And that's it.
Okay, thank you. Do we have any questions?
Too late.
Okay, thank you. We'll move on now to a presentation by Zhenming Wang, Maximum Magnitude and Recurrence Interval for Large Earthquakes in the Central and Eastern United States.
My title is Maximum Magnitude and Recurrent Interval for the large earthquake in Central and Eastern U.S. I think a previous speaker in this section today I've mentioned several times talk about magnitude. I think this is very important for the seismic hazard assessment, particularly for next, please. Yeah, next, please. Yeah, I was kind of will be cover kind of so give why we concern the maximum magnitude and recurring interval, and talk about that how what the kind of we learn right now, what we know in the central U.S. AMAX and the recurring interval, and a specific focus on pneumatic seismic zone and what we can see from there. Next, please. Well, I guess actually there's one the presentation already showed this. I think I just want to use this kind of on top of that associated with seismic hazard. You clearly see the Central and Eastern, a lot of nuclear power plant, particularly after Japan accidents, of a lot of concern in this area. So that's very, I think, important for us need to look into the maximum magnitude and the recurring interval. And next, please. Well, for me, really, I think I work for Kentucky Geological Survey, and then we have a nuclear facility. Basically, this is a particular gas diffusion plant really provide most the no-grade nuclear power material for the power plant. So this has been a really issue that I kind of deal with. And then if you look at the lower corner here, this is where relative to the pneumatic seismic zone. So it's very close there. So it depends on who you are. They can draw the line basically the active fault right into the facility. So really it's a big problem that's kind of all along. And then in this bigger picture, you see the Ohio River right here. And this is this particular gas diffusion plant. This is supposed to decommission in a few years. There's a lot of the cleanup activity related to that. So a lot of seismic design related to the facility. Next, please. And I think it's one thing when we talk about this magnitude, and also need to talk about frequency associated called recurring interval. So this is general Gutenberg-Richter relationship. A larger magnitude recurring interval will be larger. So this is general, I think is global, it's kind of relationship. Now that apply this, look into the Central and Eastern, what we see. Next, please. And I just kind of more for comparison purpose, I just take this from USGS, the hazard model. And if you look here, I think it's a 96 model. And then if you look, this kind of data is much active for the California. So you can generally see the magnitude 6, approximate in a few years. And magnitude 7, you look at the 10-year or to the decade. And magnitude 7.5, you look at in 100 years range. But if you look at central U.S. Here, and again, you look at the magnitude 6 in 100 years range, and the magnitude 7 in 1,000 years. This is the kind of directly taken from the regional seismicity. Next, please. And then now, particularly two seismic zones, I think many of several previous speakers already mentioned it. So one is New Madrid, and the other one is Wabash seismic zone. And if you look at New Madrid, this I will take it from the year 2000, that's 1996 national hazard map done by Franco and others. And if you look this the kind of Gutenberg Richter from the small event, and you project that is really, if you look at this magnitude 7, is really in a range of several thousand years. But we know also from paleoliquefaction, and then in the central U.S. area is the New Madrid seismic zone in particular, is the paleoliquefaction has played a very key role to determine recurrent interval. And then if you look at Wabash, you compare these seismicity, small earthquake, and compare to the kind of paleoliquefaction, it's sort of there is a comparable. And again, if you look at the kind of the overall rate as magnitude 7 or above, the recurrent interval in a few 1,000 or few thousand years. So that's general kind of consistent. But now, let's closer look at why there's inconsistent there. Next, please. Well, I guess the other the study also, this is the Calais and Stein from GPS. From the GPS rate, it's kind of give you where the kind of the magnitude versus the recurring interval. So if you talk about 7.5 large earthquake, really GPS gave you, you're talking about, again, in 1,000 to a few thousand years, the years of recurring interval. And the same thing, actually, there's also another paper, actually two papers, actually, Lee and others, doing they call more a dynamic modeling. If you look the model, they result the same. Again, it's look at 7 and larger, also in a recurring interval in several thousand years. Next, please. And then now take a look at the liquefaction, paleoliquefaction. I think this really where they make a big difference. And if you look, this is the Tuttle and others by the year 2002 publication. But again, if you look at their date, really large uncertainty in there, particularly if you look at this event, very all over the place. Next, please. So what the paleoliquefaction study, I just kind of, this is also from the paper, kind of look over where liquefaction they saw, really in a very, very active New Madrid zone, also is very, very active the Mississippi River floodplain. And this is kind of what the paleoliquefaction feature look like. And next, please. Well, I think it's one thing, last year, Mississippi, there's a big flood. It's called the 100-year flood. And this is kind of where the flood area. It's very, very comparable to where paleoliquefaction found. And next, please. And right now, if you go to Google, actually, you can see many sand boil from last year's big Mississippi flood. Many, many places. I just show you two places I see. One is over here, and the other one is Carroll here. And because I will focus on here. And so if you go to Google Map, blow up here, you can just along the Mississippi River from Carroll all the way to the Memphis. If you carefully look over along the levee both sides, you will see many, many sand boil. Right now, actually, if you go into Google, you still can see it. So really, a lot of sand boil. When this earlier, I run into, because we have a station out here, I run into a core engineer, a geotechnical engineer, and he showed me the sand boil. I said, wow. And then I said, well, can I see that? He took me over there to see it. And then he also told me, you got this sand boil, you see all the way from here to it. You can see everywhere you see. But every big flood, they deal with that. So next, please. So this is kind of, if you go to Google, this was once 2001 is the Cairo, and you see this is still on Google. You can still see a lot of sand boil in Cairo, and this were in Kentucky, and you see this is a kind of sand. This is actually, if you blow up, you still can see sand boil over there. And next, please. And here's the photo when they had sand boil. This you can see it, and this is a photo taken by the Fulton County, the emergency manager. They see here, this is it, when that sand boil occurred, and this is a lot, it's many of them. The reason they put the sand the back there because they were afraid of if keep running sand boil and they could breach the levee. So they had tried to knock that sand boil the running. So that's why they're doing that. Next, please. And again, if you look at the history, actually, many the Corps engineer they deal with this sand boil almost every flood, not necessarily historic flood. And you see, this is one actually it's not a historic flood. 93 is a flood, Mississippi flood, and then Lee, and that's published paper. You see, this is the sand boil. Still, you see in the ground. And the Corps engineer actually, this way earlier, they actually, but this is the 93 flood. They see along the Mississippi River and along the levee, this sand boil actually quite often you see it. Next, please. And then this is from the Corps engineer that they actually published a whole report back the 1973 flood. So really, they actually found many areas have a sand boil. So they actually had to develop a mitigation how to deal with that because if that is a serious sand boil could breach the levee. Next, please. So clearly, is particularly in the Mississippi embayment area, with a so active flood and meandering, and this the sand boil is really everywhere. So I think it's clear that here is a summary. Maximum magnitude and recurring interval is very two key good. I think it's very important parameter for seismic hazard and risk assessment in the central and eastern U.S. So a lot of time we only talk about maximum magnitude, but also we need to look into the recurring interval because the two parameters go together. Large magnitude, yes, could occur, but also very long recurring interval. And then based on the many study, again, if you look at GPS and the several talk and other study, you can see this large earthquake, magnitude 7 or above, the repeat time is longer. It's in the order of few thousand years. So this is a consistent. The only thing inconsistent is a paleoliquefaction study. And then now you can see, if you look at pneumatic, earthquake-induced liquefaction in a pneumatic seismic zone may be contaminated by the flood-induced liquefaction. So I think it's the bottom line here. The result from the paleoliquefaction study in a pneumatic seismic zone need to be re-examined. Thank you.
Thank you. We have time for a question. Beatrice.
Well, I guess it's so frequency. If even no levee, small, naturally, some levee still can produce some liquefaction. So it should have a consistent check. It's compared is hydraulic. This hydraulic origin compared to the seismogenic. Particularly in the pneumatic, you see, so active at the flood. But also you see all the liquefaction site all along the very close to the river. If you look there, actually maybe go back to the where's the map there. Go back to, go back the first one, maybe further, go back, yeah, all the way back. Yeah, right here, right? Yeah, here. So if you look at the side, also very close to the river. It's not kind of far away from the river.
Okay, we'll have to. So this is an interesting discussion. I think we'll have to continue it afterwards. Thank you. We're moving on to the next to the last talk, and I'll remind you that we will have a student talk at the close of the session. So next we're going to hear from Morgan Page. Can current New Madrid seismicity be explained as the decaying aftershock sequence?
Okay, so the short answer is I don't believe so. So this hypothesis has been around for a while. It was first laid out rigorously by Abel et al. 2000, and they have this nice paper, they call it paleoseismicity. So it's a rather clever idea that if you knew that all of the earthquakes in a given region that would otherwise be quiet were due to aftershocks, you could, based on the length scale of those aftershocks and the rate of those aftershocks, determine the time and approximate magnitude of a large event in the past. And they apply this both to New Madrid and also to other regions to infer events that occurred even before the historical record. So I'm sure you've all heard of the Amori law as modified by Utsu here. This just basically shows that the rate of aftershocks over time decays as approximately 1 over t. The p-value, this exponent here, is usually found to be around 1. So it's important to realize that when people normally refer to the Amori law, they're referring to the indirect law. So the Amori law that you would measure directly from a catalog includes the total rate from direct triggering from the main shock and also second triggering, which is the aftershocks that the first generations of aftershocks trigger and subsequent generations. So what you measure in a catalog is not only aftershocks directly triggered by the main shock, but a number of generations of aftershocks. This is in contrast to the direct Amori law shown here. The direct Amori law refers to just the rate of earthquakes that are triggered directly by a given earthquake. So in this case, this is the first generation of aftershocks that can be attributed as directly triggered by the main shock. So these would follow this top black line here. And then the next generations of black lines are earthquakes triggered by the first generation of aftershocks, because all earthquakes will trigger aftershocks to some level. And then the following lines are subsequent generations. So if you add up all of these black lines, all of the direct Amori triggering, it adds up to this red line, which is the well-known indirect Amori-Utsu law. So it's important to notice I'm going to be doing some ETOS modeling here, and the parameters we'll be discussing relative to this epidemic-type aftershock sequence modeling. Most importantly, the A value here, the productivity, and the decay constant P are the direct A and direct P, which are different from the indirect A and P that you'd measure from the red line. Although at long time periods, the long-term P you'd measure from a catalog matches the direct P. So the idea in ETOS modeling is every earthquake triggers aftershocks in proportion to 10 to its magnitude, and we're going to add all these up and try to recreate the statistics of the entire sequence. So you can't just pick any parameters you like. If you try running an ETOS model, you'll discover that if you set certain parameters incorrectly or make the sequence too productive, the whole thing basically blows up. So this is showing in phase space, this is the p-value here, that exponent, and the productivity, A value here. There's a whole region of phase space that is supercritical, which means if you are in the supercritical, this red regime, each generation of aftershocks will trigger more earthquakes on average than the previous generation. So in that case, your sequence would just quickly blow up. Your second generation aftershocks will have more earthquakes than your first generation, and so on. So that's very unphysical. Any real earthquake catalog would have to be in this white region here. And just for comparison, the red dot shows average direct A and direct P values derived for a California data set by Felser in 2003. So I'm going to recast the question of in my title, can current new Madrid seismicity be explained as a decaying aftershock sequence, as can we model the new Madrid sequence with one set of indirect Omori parameters? So can the whole sequence be explained as entirely aftershocks matching some indirect Omori sequence, although we're going to solve for what the parameters could be? And our goals here will be to, of course, stay subcritical. We don't want an infinite number of aftershocks. And to match clustering seen in the early sequence, what I'll discuss shortly, and to also match current seismicity rates without adding any background. So if you assume that all current seismicity is aftershocks, can you make it fit? So I'll be matching seismicity in this CSSSE catalog here. For the bigger box here, you can see this is what a lollipop diagram showing seismicity looks like. Here's the cluster of earthquakes here that happened in 1811, 1812. Of course, their magnitudes are very uncertain. There's a lot of debate about how big those events were. What's much more better determined is the relative magnitudes of those earthquakes, which is what I'll be trying to match. And of course, early in the historical catalog, we only know about the larger events. And then in the instrumental period up here, we do very, very well. In this large box here, we have 6 earthquakes in this 10-year period recently, above magnitude 4. Going to the smaller box, which is what I'll be trying to match, you get about 3 earthquakes in a 10-year period. So as I said, there are several unknowns here in what we're trying to match. Those early magnitudes are very uncertain. And of course, in the early parts of the catalog where we're relying on historical data, we don't know the rates of small earthquakes very well. So our goal is to basically match the parts of the sequence that are best constrained and best known. So of course, we can't match these because we don't know these very well, but we do know the relative magnitudes of the early cluster well. So there was a cluster of these 4 earthquakes with very, very similar magnitudes, and it appears that these are not just something that happened in 1811, 1812. In fact, paleoseismic evidence from Samblo evidence indicates that the previous sequences, again, these sequences happen every 500 years or so on average, they also consisted of several large events over several months. So it seems that this is really the norm for this region. So that's something we definitely want our ETOS modeling to capture. And the other thing main thing we'll be trying to match, which is a well-constrained thing, is the current seismicity rate near New Madrid. First, to show as a comparison, here's what ETOS simulations look like for a magnitude 7.6 main shock with California-derived ETOS parameters for a 200-year period. So you can see this is the 1 over t to the p fall-off. The blue line shows an average of many ETOS simulations. You just get they're inherently stochastic, so each time you run it, it comes out a bit different. Here is the rate from the New Madrid sequence plotted on the same graph. So this is seismicity early in the sequence was very active early in the sequence with 30 to 65 earthquakes above approximately magnitude 4.6. And again, there were at most 2 magnitudes 6 and greater earthquakes after a year 1 to 100. And here are 2 current estimates for the more recent rate of seismicity. And the main thing to notice here is that the red tends to be higher than the blue. So we can already see we're going to have to do something special. It's unlikely that California parameters are going to match this sequence, which you'll see. It really is more productive early in the sequence. And if you assume that these are aftershocks, it's also more productive than you'd expect with California parameters. So California parameters aren't likely to work. What about other parameters? We'll search the phase space, again, to match these 2 primary things, early clustering in the sequence and current seismicity rates. Here I'm showing, I've sampled this space by running thousands of ETOS simulations at each of the black dots. And then in those simulations, I pull out the percentage of those catalogs that match what I'm trying to match in the real New Madrid sequence. So this black line, above this black line, 5% or greater of the catalogs had 4 shocks within 0.5 magnitude units within the first 2 months. And this line is a little bit noisy because I'm only sampling at these black points. It takes a lot of computational time to run all of these 200-year ETOS simulations. But we can see the approximate region of the phase space that matches the early clustering that's seen in the New Madrid data. And the other thing we want to match is the relatively high rate of magnitude greater than 4 earthquakes that are continuing in this region 200 years after this set of shocks. And in order to match that, we have to be over in this area of the phase space. So again, this is an area where at least 5% of the catalogs would produce a current rate of earthquakes matching what we see in the New Madrid region. And what I've tried to do here is in every way give the hypothesis the best chance of succeeding by, for example, for this test, picking a very large magnitude, as large of a magnitude as is reasonable for the main shock, and making that box, which I'm drawing current seismicity, as small as possible. So there are a few tunable parameters, but I'm trying to tune them in a way to give the hypothesis the best chance of being successful. So far, just from those 2 bits of data, we are left with this allowed region, shown here in purple, that matches both the current seismicity rates and the short-term clustering. So what about sequences in this remaining allowed region of the phase space? Do they look like New Madrid? Well, no, not really. So, for example, just at this, in the sequences at this point here, we get a fair amount of sequences that do match early clustering and current seismicity rates, but they also do not match other aspects of the New Madrid sequence. First of all, the largest earthquakes in this range are extremely high, much higher than we think the New Madrid earthquakes probably were, and higher than we've seen in the intervening time, most importantly. So these earthquakes are extremely active. Yes, they're in the subcritical regime of the ETAS modeling, but only just. So they're producing extremely high numbers of magnitude 6 earthquakes as well in the intervening time between a year after the 1811-1812 sequence to present, ranging from, of the thousands of sequences I looked at, the lowest one was 6, and many of them were in the hundreds. And looking at these other points, and I wasn't able to find any sequences that were similar to New Madrid in the intervening time. So most of these sequences here have dozens of magnitude 6 and greater earthquakes occurring a year after. So they're so productive. They're not just productive early in the sequence and late in the sequence. That naturally forces you to be productive throughout the sequence, producing a greater rate of magnitude 6 and greater earthquakes than has been observed. The New Madrid region has had 0 to 2 earthquakes in this time. It's a little bit uncertain because magnitude is uncertain, but it hasn't had more than 2, we would know from the historic record. So then, just to summarize this, sequences that match, high rates of clustering early in the sequence and also high rates of current seismicity late in the sequence, that pushes you up to a productive enough sequence throughout that you really produce too many moderate earthquakes in this intervening time that we don't see. So I've shown that the New Madrid sequence is statistically different from aftershock sequences with a single set of direct Amori parameters. So, of course, you could always say, well, perhaps the direct Amori law is not applicable in this timescale. We're extending out this statistical empirical law to timescales of 200 years. But it would be very surprising. It's one thing for something to have a roll-off and, a few 200 years later to not completely apply. But for that statistical law to underpredict the rate, for actually say, yes, it goes as 1/t and then actually bumps up, that would be really surprising in my opinion. So I believe that this really shows that these earthquakes are not aftershocks. They don't follow Amori's law, and it seems that they must be background events. There must be continuing strain in the region. So I would say this points to the idea that it's unlikely that the sequence will continue to decay, since they're not only aftershocks, and the hazard in this area will continue. Thank you.
Thank you, Morgan. We have time for a question or two. There is one. Okay, late on Friday, we are down to the last talk of the session, and I'd like to ask Azadeh Faridoni to now present statistical features of aftershock temporal behavior in the St. Lawrence Valley.
Good afternoon, everybody. Thank you for listening to the very last talk of the AGU. In the next few minutes, I'm going to talk about the result of a study which was done as a part of my PhD project under supervision of Gail Atkinson. And yes, thank you. Sure. And I will show you how we use the history and pattern of the seismicity in the St. Lawrence Valley, which is the most seismic active region in the eastern Canada, to gain a better understanding and interpretation of the seismicity, current seismicity in the region. Next, please. The study was originally motivated when I faced a challenging question in my PhD project, which was estimating the earthquake hazard in east of Canada. If you, excuse me, can I have a pointer? Oh, thank you. If you look at the National Hazard Map of Canada, you can see the level of the seismic hazard in St. Lawrence Valley is the highest one in eastern Canada, and in some regions it is as high as it is in West Coast. If you look at the seismicity map along the St. Lawrence Valley, you can see the seismic activity is clusters in different seismic clusters along the valley. With the shallow seismic zone being the most active cluster, the epicenter of the magnitude 7.60 earthquake has been located in this seismic region. But the reason behind the earthquake clustering along the valley is still poorly known. In 1980s, Adams and Beauchamp proposed the idea that the current seismic activity in shallower region and along in other clusters along the valley might be the long aftershock sequences of past large earthquakes in the region. After 2 decades, this idea is still in debate among the scientists who are involved in the earthquake hazard assessment in the region. So to answer this question, we decided to look at the seismicity pattern of aftershock activity in the region to see how the aftershock activity die off with time in the St. Lawrence region. Next, please. To do that, we decided to use the modified Omori formula to model the decay pattern of aftershock activity. And in this formula, like Morgan said, the frequency of aftershocks is modeled by this formula, and K, C, and P are constant parameters that need to be determined. Here you can see the decay of aftershock activity after the Val-de-Beau earthquake 2010 near the city of Ottawa, which is modeled by using modified Omori formula. After obtaining the parameters, we examined the goodness of fit using the residual analysis of aftershock. This statistical analysis was introduced into aftershock studies by Ogata. He used this method to study the aftershock of Rat Island earthquake and to detect the ending time of this aftershock activity. Afterward, this method has been used widely worldwide. But as far as I know, our study is the first application of this statistical method in Eastern North America. Like I said, after obtaining the modified Omori parameter, the integration of the rate function in residual analysis produce a transformation from the ordinary time to transform time, which is called tau in this analysis. Next, please. If the obtained parameters is appropriate for aftershock data, then the cumulative number of aftershock against the transformed time forms a linear trend. And moreover, this linear trend continues until the ending time of the aftershock sequence. So this method provides a straightforward but subjective approach to detect the ending time of aftershock sequences. Next, please. Next. To perform this analysis, we gathered our database using a primary source of earthquake, a composite Canadian seismicity catalog, and we enhanced our database using additional sources. All the magnitudes from additional sources were converted to moment magnitude to keep the consistency with the primary source using the relation that proposed in Freyduni others in 2012. Next, please. Because our database covers a long period of time from 1500 to present, and obviously the quality of earthquake reporting is not uniform over this long period of time. So we looked at the quality of earthquake reporting over time by assessing the magnitude completeness of our database in the entire St. Lawrence region in general, and also in the Charlevoix seismic zone in particular. Next, please. Here you can see our estimation of MC values in the last century from 1900 to 2010 in St. Lawrence region and Charlevoix seismic zone. And as you can see here, in the entire St. Lawrence region, the MC values vary around 2.6 per year 1980, and after that gradually drop as it is expected. When we wanted to perform our analysis, we picked the magnitude completeness for recent aftershock sequences from this data, from this plot. But for the past earthquake, we choose that values subjectively based on the availability of the data. Next, please. Here, in the next few slides, I will show you the steps that we carried out in our analysis to find the statistical properties of aftershock sequences using the 6063 Charlevoix earthquake as a representative example. In the first step, I fitted the modified Omari formula to the aftershock data in the first 500 days after the main shock. Next, please. And I obtained the aftershock parameters, the modified Omari formula parameters, by the maximum likelihood estimation method, which is also proposed by Ogata. And then, next, please. And then I look at the goodness of the models that I obtained using the residual analysis that I talked about it previously. Next, please. Here you can see the cumulative number of aftershock sequences, cumulative number of aftershocks after the 6063 earthquake into two different time scales. In the right against the transform time, and in the left against the ordinary time. And as you can see here, the cumulative number of earthquakes forms a nearly linear trend against the transform time, which should suggest that the obtained parameters are good approximations of the true model. And next, please. And clear change in the slope that can be seen around 200 years after the main shocks ends the transition time from the aftershock activity to the background or normal seismic activity in the region. Next, please. We wanted to find out if the result that we have obtained about the transition time is sensitive to the cutoff magnitude that we have considered in our analysis. To test that, we repeated data for two higher cutoff magnitude greater than 4 and magnitude greater than 4.5. And as you can see here, stability in the result and transition time leads us to conclude that the aftershock activity of 6063 earthquake ended about 200 years after the main shock. Next, please. We also performed the same analysis for other major earthquakes in the St. Lawrence region, and the duration of the aftershock, which is plotted here against the magnitude of the main shock, varies between a few years to 200 years for the 63 Charlevoix earthquake, which could be considered relatively short duration for overall aftershock sequences in the region. And it is also quite interesting that the duration of the aftershocks appears to increase. Next, please. Increase with a linear trend against the magnitude of the main shock. Next, please. The other interesting result that came out of the study was the general seismicity in the aftershock parameter, which is plotted here for p-value and k-value, and it also could be considered as a characteristic of the seismicity regime in the St. Lawrence region. Next, please. So in my conclusion, I've shown you that our study revealed that the aftershock sequence of the 6063 Charlevoix earthquake lasted for about 200 years after the main shock. And we also found that the aftershock sequences in the St. Lawrence region have relatively short duration. So based on this observation, we concluded that the current seismicity in the clusters along the St. Lawrence Valley are not the decaying aftershocks of past large earthquakes in the region, so they should be considered as part of the seismic hazard in the region. We also found out that it seems that the duration of aftershock sequences increase with the magnitude of main shock, but we need to look more into this conclusion. The other interesting conclusion of the study was that the aftershock sequences in the St. Lawrence Valley seems to share the same value of modified Omori parameters, which could be considered as a characteristic of seismicity in the region. Thank you.
Well, thank you very much for that great wrap-up to what's been a very stimulating session today. Do we have any questions? Well, if not, thank you all for attending this session, and we look forward to seeing you in San Francisco next year, if not sooner. So, thank you.